Good morning, everyone. I'm Christopher Drew, and today you're here, hopefully, to learn about how we're applying neural radiance fields to building 3D models of shipwrecks. But there's one more thing, because since we filed the application for this panel, our research has been continuing, and we've also found a way to do Gaussian splatting as part of that workflow. We'll get into a lot more detail soon. But basically what I'm saying is this is going to be one hurricane of a 45 minutes. And afterwards, we'll have Q&A outside, and we also have a website we're going to give you with all the lab notes, etc. So, for those of you who are furiously taking notes and photos, I have really good news. You can relax and enjoy the presentation because at the end, the slides will be online. This QR code will be up at the end as well, so no rush to get your phone out if you're trying to scan it. Everything we're talking about today is free, open source, and any outputs are Creative Commons licensed, which means the whole reason we're doing this is to make it available to the world for public good. What we're going to talk about today is a fair bit. Obviously, some introductions, why we're here in the context of survey, and then we're going to talk about neural radiance fields, what they are, why they are, and how they're done, and then we're going to talk about Gaussian splatting and some of the improvements that brings to survey as well. But before I even get into that, I want to really emphasize that I am not here in a vacuum. I am here with the entire Scuba.Tech team, and they support this mission, and we all have strengths that contribute to it. So I want to do introductions and credits at the beginning, not at the end, to emphasize that. I know that's a little backwards unconventional, but I want to credit everyone up front before we even get started. As for myself, I'm Christopher Drew. I'm the president of Scuba.Tech, and I also serve in the team as a director of ROV operations, and I also serve as the diving mission controller. Next up is Josh, if you want to just stand up and say hi.
Hi, my name is Josh Gross. I'm the vice president of Scuba.Tech and the head of research and development.
Awesome. Next up is Henry, who's furiously working on a lab right now.
Hello, I'm Henry. Nice to meet you.
He's also our tech for field operations, and he's also learning to be an RV engineer. Next up is Sydney.
How you doing? I'm Sid, treasurer, historian, old guy on the team.
And next is Jesse.
I'm Jesse. I do research and development and kind of technologist.
Yes, and then for the next introduction, he couldn't make it in today. He's remote, but we have Paolo. He's our public relations manager. He helps make the research we do a little more friendly to the rest of the world in terms of engagement, and he helps with our video production. We're also a bit of a spoiler at the end. I'm going to show you a slide with the YouTube channel. We're turning a lot of this into video tutorials as well. Next up is Adam, who's joining us remotely from near Chicago.
Hello, everyone. I'm Dr. Adam Schreckenberger, a particle physicist at Fermi National Accelerator Lab. That's the place where protons go burr in a circle really, really fast. So you're probably wondering why I'm here. There's plenty of reasons, but the biggest one, thank you, Henry. I'm a particle physicist. There are particles in the ocean. That's synergy, baby. Let's go. So enjoy what my colleagues have put together for you today. Esteemed members of the audience, it's bubble time. Back to you, Chris.
Thank you, Adam. None of that was planned. But yeah, he's a particle physicist. He's a resident mad scientist. And on a more serious note, he helps make sure that what we do is scientifically accurate, both in terms of how we write it up and publish it. But he also helps cross-check a lot of our methodology, especially when we get stuck somewhere in a Linux console, and helps us kind of get through that. Next up is Andrew Huebner. He is not able to make it today. He's at University North Texas, and he's also a historian who works with the National Archives by DC. So he helps us with a lot of our formal history and historiography and background research. Next up is Justin, who you saw setting up all the tech. I know you're very busy. He's amazing. He's our director of cinematography in the field for our events. And then last but certainly not least is second Andrew.
Hi, I'm Andrew Agnew-Stewart. I'm a part of the post-production committee as a volunteer staff member on Scuba.Tech. I make a lot of the videos on the YouTube and work alongside with the whole team here.
Awesome. Thank you so much, folks. I'm going to go ahead and give you a front row seat. All right, so you know who we are. It's probably better now to talk about what we do. So Scuba.Tech is the name of this nonprofit, non-stock incorporation. We are 501c3 compliant. For anyone who's worked with nonprofits, we're currently going through the Form 1023 audit and recognition process. So I'm sure for 4 people in the room that hopefully shares the communal pain. But the point is we operate in a completely nonprofit, public good purpose. And our mandate is pretty simple, and it's one thing that we all had in common because we were doing this informally as a group of friends for nearly a decade before we decided to incorporate. And that is, we want to increase community stewardship Starting off in the New York City tri-state region with the marine ecosystem, this is a very, very lush bioclimate, and there are so many students in middle and high school and even college who haven't yet had that exposure to be on the shoreline. We partner a lot with the New York State Marine Education Association to that end. The next thing that we're focusing on is promoting the fields of oceanography and marine biology. Pretty self-explanatory, but we want to kind of close that knowledge gap intergenerationally. And then last but not least, and kind of the reason why we're here today, is we're doing R&D for new workflows that combine historiography with technology. That's kind of broad, but that's the umbrella we operate under. In the context of today, the way we're doing that is we're working on augmented and virtual reality experiences of shipwrecks, and that could be used for archaeology proper, or just because it looks really cool and it's fun to bring into the classroom environment. So what we're going to present today is some of the better work that we've done towards that end. Now, I also want to credit a lot of volunteers on the Stolt 3D expedition. You're going to see some outputs from this effort. We are all working together, and I would be remiss if I don't credit them up front. Some of the 3D data that we are presenting, they have gathered a lot of the source photos coming with us on the Stolt 3D expedition. So I want to also present our extended team and say thank you on the record, both video and in this room. Okay, the last thing I want to credit before we finally get into the lecture is some of the organizations that we've taken knowledge from and built on and then synthesized. So we have the University of Cyprus, and that's with Dr. Stella Domestica. We have the Mare Lab. We have the Nautical Archaeology Society. That's with Mark Betty Edwards. We, of course, have New York State Marine Educators Association, Stevens Tech, Big Apple Divers, NBC Dive Voyager Expeditions. Captain Steve and Maureen Langevin are the ones who actually gave me that first chance to get in the water. And then the New Jersey Maritime Museum. Deb Whitcraft was my inspiration for getting into maritime history. Let's talk about what we're here for now. Survey. Just a quick show of hands so I can know the audience better. Who here has any experience mapping, sketching, archaeology, tape measurements, any? Okay, 1, 2, 3. We'll round up to 5. It's 4.5. So for those who have not, there's a lot of ways to record a site, and the reason that's important is to capture the context of the site before we would do excavation, or perhaps just share it with the world if it's something that's really worth sharing, especially in the context of marine heritage. But not just cultural heritage, but it could be a biome. Maybe you want to share the condition of a reef or something, right? So we have site sketching, which is very contextual, which is a polite way of saying sloppy, but good for awareness. But it can be pretty quick. And then on the complete other end, we have precise techniques such as lidar fusion, neural radiance field, Gaussian splatting, photogrammetry. I'm a little biased because those are the ones we work on. And then we have speed, glacial versus rapid. For those of you who've done trilateration or baseline offset, which is measuring tapes underwater and you're writing on vellum and then you go ahead and you scale it topside, as you might know, to do a single shipwreck field could take years. On the rapid end of things, we got multi-beam synthetic aperture sonar and side scan, which is real time. What we're presenting today is somewhere in the middle. The data capture is very fast. The post-processing can take a few days, but it's done digitally. Okay. So a very abridged process of what was the state of the art last year is photogrammetry. I am not going to go through the photogrammetry curriculum because that's a 6-hour class, but to give you a very abridged process, we have a dive site. We take a series of overlapping photos that have at least 70% overlap between shots, vertical and horizontal from different passes. We then import and align them through a series of mathematics, or we take contrast point pairs and we can match them to get stereoscopic information the same way your eyes work. And then we can project that into a series of depth maps. You intersect the depth maps and you find those intersections and you have a point cloud. It's a series of coordinates in 3D space. It kind of looks like colored grains of sand. And then from there, you would build a mesh where you link them all together, and then you would apply a texture map, and there you have a 3D model that you could use in a game. That's incredibly abstract, but that's the current state of the art, is building a 3D model of a ship where the 3D model is an object, right? A discrete object, like you would imagine a 3D model to be. But to give you a little more context on the human element, how it looks, who here knows Larry? Okay, all right, fair enough. Well, he's taught me most of what I know about underwater photography, and he's also one of our volunteers with the Stolt 3D expedition. So in this case, I'm using Larry as an example. The photogrammetric process, like I said, you're circling around a shipwreck. This is the SS Red Wildland Spot made by Mike's daughter out of 2 A-spin trash cans and some duct tape. And as you can see, those photos, as they're aligned in 3D space, are projecting those point clouds, which are then meshed and textured. I want to give credit to the girl who made the shipwreck for us to train on. So you have some really cool advantages with photogrammetry. You've got really good texture detail. This is all digital. This is not a picture. That's just a render from the model. But anywhere that there's incomplete data, it gets really glitchy and peely and jagged. and we're going to actually fix some of that today. So, the Stolt 3D expedition in the context of photogrammetry has 3 goals, right? The first goal is we want to do the photogrammetric capture of the Stolt Shipwreck. This is just for anyone who didn't make last year's panel, so you know what we're going to talk about next. The second goal was that it would be digitally native, so we can transport that asset and distribute it worldwide, have it embeddable through ARKit on your phone, tablet, or Apple Vision, or through Android VRKit. And then we want to make it an open survey model where we publish our entire workflow. So we're about 2/3 through that. This is traditional photogrammetry, and when we apply it, this is what those transect passes look like top down over the Stolt de Gali by photo. And then taken away back into the picture, that's the photo view. Multiply that by 7,500. So on those photos, we do a little bit of masking. We remove bioclutter, which can introduce temporal anomalies when you start doing comparisons and trying to get stereoscopic data with things that move. So we mask out the fish, we mask out the glare. And then after, I'm just kind of skipping 4 months of work, we start to get these beautiful point clouds. These are 3D models we can rotate around. And we can also link these scale bars that we place on the rack for X, Y, and Z axis. That one's kind of up at 60 degrees. We can link those, scale the model properly. And the picture in the bottom right corner, I just kind of included so you can see what that process looks like from a diver's perspective. But it's not just good for macro elements. We can get into some detail elements. Macro meaning at scale, not macro photography. So now we have some detail. Show of hands, who's dove on the Stolt de Gali? Okay, a fair amount. Right on. Actually, I think I have some of your photos. So this is the rear skylight. I believe it's right above and behind the kitchen, if I remember right, the galley. And we kind of have this hat pattern where we're capturing the photos from every angle, ensuring good overlap. And when it's rendered, this is what an output would look like. So here's the rear, that skylight, that stern skylight that everyone loves to visit, rendered out in photogrammetry. And I want to point out that when you have good visibility, and when you have a good photo overlap, you get incredible detail. And you even have the 3D modeling of the actual, anemones and starfish and everything that's living on it. Moving forward, taking that detail to the hull structure itself, we're currently in the process of mapping out the shape of the hull. We're in the process, we can even get as far as to count the number of anemones, and we could train a model to count those if people want to know how the biology changes over the years. But even cooler, we're starting to capture a lot of the larger geometry coming towards the stern. So as you know, the cranes are going to start to appear down here as we keep going. The skylight we were just rotating around is right here. And then here's the railing going up, and the promenade starts up there. Now I've just moved the camera forward another 40 virtual feet towards the bow cut and then rotated looking aft. So you can kind of start to see the promenade. And then here's the forward cut. For this particular photo set, great credit to Joe St. Amand. He helped us to figure out the lighting system that would let us capture that without too much specular return or backscatter, which ruins the data set. But there is a few tiny things we can improve on. First of all, you notice it looks kind of grainy and there's some gaps where the data's not perfect or it's hazy or silty. The computer can't match the reality to the digital model very well. So let's look at other methods. Well, the title slide kind of gave it away, but we're going to next talk about neural radiance and Gaussian splatting, right? So, what is a neural radiance field? We're still building a 3D scene. That hasn't changed. We're still taking a bunch of photos of the wreck. The how particularly is going to be on the website. But instead of building an object, we stop caring about the object. We're building a light field. We're taking a 3D box of a scene. It could be a vessel, it could be an artifact. And in that 3D box, we're calculating what is the light doing, the photons, what direction, what color. We're doing reverse ray tracing. Until very recently, that kind of compute was considered impossible. What we do is we use those aligned photos as viewports to do, think of like, for anyone who works in finance, you could do like a back test to check a theory. We're basically back testing a radiant output against a neural model's implementation, and we keep refining until we've built a light field in a 3D box that matches reality. Greatly abstracted, but basically we don't care about the object, we only care about the light and the environment, and then we can get that object inferred from what the light's doing. And it's really good for fine details. For those of you who've tried to survey things that include ropes and rails, a lot of those kind of get clippy or spatially aliased out when you try to turn that into a model. This solves that problem. But it's better to show than tell, so I'm going to show you what it looks like. When we make a neural radiance field, the input is the same. You have a set of photos that go around. In this case, it's the silver comet. It's a great training wreck at Dutch Springs, now Lake Hydra. And we chose that site because it's accessible, it's a decent size, and there's a lot of detail to capture. And more importantly, there's a lot of fine detail that can't be captured with photogrammetry very well. So it's a perfect test candidate. So we take those photos, we do a lot of our work in NeRF Studio, which is a suite that presents as a web UI. It runs in a Docker container. If those words mean a lot to you, I have really good news about our lab notes because we're going to show you every command line to instantiate that environment. And then after NeRF Studio, we can do our final render of this trained field. So I think it's time for a comparison to really show you the why. I've talked a little bit about the how, right? So exhibit A, we'll call it. This is the Silver Comet as a photogrammetric model. Now notice where the data is really solid. We've got really good detail. Those scale bars, X, Y, Z, are fantastic. This railing is fantastic. The side rail that's falling off to the floor is fantastic. But where we have haze, say silt from a class that swam by recently, the haze starts to corrupt the model because the computer's now trying to interpolate as best as it can between matching data. And where we have fine details with the hazy environment, it just creates a flat plane and textures it as best as it can. And you can edit that with any mesh editor. We could throw it in Blender. There's a whole suite of tools, but it's incredibly tedious. But we can do better. I also want to point out that where there's data missing entirely, it'll kind of crush the model to try to force a solution, which, to be clear, is the best outcome. I'd rather have it do that than fail a render. So where the current state of the art, I should say last year's state of the art, is really good for general survey and awareness. And if I do an orthophoto mosaic top-down view, this will look fantastic. But we can do better. And I would like to show you next, based on a lot of our research to make sure of this before I say it out loud, what we believe is the first ever neural radiance field of an underwater vessel in its entirety. We finished this November, and we've been refining the workflow between then and now. So without further ado, the first neural radiance field of a complete underwater vessel. I want to point out the ropes were not aliased out. I want to point out that some of the haze you're going to see over the cabin just is rendered as haze. What a concept, but that's nearly impossible for computers to do until recently. So that particulate, that haze, is just what it is. The railings are perfect despite discontinuities in the data set. All of the details and textures and bump mapping and hardware on the deck, including the cleats, are done perfectly. The rails don't occlude out of view, nor are there flat planes obstructing the view through them. You can even see through the windows. They're not flat planes anymore. And then where the silk clouds were kicked up, well, the computer just treats it honestly, and there are silk clouds. And we circle back around the front to complete the tour of the Silver Comet. So this is a Neural Radiance Field 360 render. Nothing that you're seeing right now is a native photo or video. This is completely synthetic. To be clear, dimensionally true and textured true, colors, this is reality, but it's a synthetic view of the radiance field itself. And I want to emphasize one more thing, because we are so proud of this. The railings in particular, having no discontinuities, no occlusion, no spatial aliasing, it's a big deal for anyone who does marine survey, because that same level of fine detail from a photo set translates really well to reefs, especially reefs with fan corals and stuff like that, or anything with reflective surfaces can now be accurately captured. And with only just a few good photos that shows this work deck, we're still able to get an accurate model representation of that deck, which means a sparser data set can now be useful. In photogrammetry, you'd usually have to throw that data set away. Okay, everything I just told you, we're calling Project OSIRIS, Open Source Immersed Radiant Imaging Survey. To anyone who's ever applied for grants, you know that a really cool project name really helps with engagement. So Project OSIRIS is what we're calling this effort to create a fully published open source workflow, start to finish, to create a radiant field of an underwater asset. But I've been talking for a while, and who better to tell you exactly what a radiant field is and how we're doing it than my research and development manager, Josh Gross, and our technician and technologist, Jesse Stevenson. Take it away.
Thank you. Well, Chris, you've done a wonderful job explaining all of the background concepts for NeRF, but I'm going to break it down in simple layman's terms for us. We're taking all of those aligned cameras from earlier, placing them effectively around where we think the object is going to be, and creating new views between those angles of that object. That is what the radiance field is being trained on. Now, it is a reverse ray trace, so you're going to basically take the light beams and infer where the object is from those light beams. But from a simple conceptual baseline, that is what it is.
So why are we looking at NeRF? I mean, Chris has talked about a lot of that already, but mainly we had a desire to look for new techniques that would work a lot better, have less time, take less time for us to make them, and also have better fidelity of the model. So from a first principles perspective, we just have to take the images in and generate a scene. We don't necessarily need to make a model. So it also eliminates a lot of the issues, like Chris said. The thin features are rendered a lot better. Also, it's less susceptible to a lot of the small temporal anomalies, so we don't have to spend as much time to filter those out of the images or crop them out. We just need to crop them out enough for the alignment to happen correctly. All right, I'm going to move on to the next slide.
So how are we doing this? We're taking an old Intel NUC 11 with an old i7 CPU and roughly 2.5 terabytes of storage. We're running this on Linux with some Docker and NeRF Studio developer software support. But we really needed to stretch as much as we possibly could to afford that GPU, which is where all of the processing is happening here. Next slide.
So I'm just going to talk a little bit more about NeRF Studio. This provides a standard method for us to try these different methods of NeRF and of Gaussian splatting, which we'll talk about in a little bit. The full environment lets us just create align the photos and do the training of it and get the outputs all through kind of the same commands. So it's a lot easier for us to try different things. For the NeRF workflow, it's very similar to the photogrammetry workflow. The main differences is the masking's only for alignment, and the photos can also be frames of a video because the first step in the NeRF is to scale them down.
NeRF Studio is the developer platform, but inside that developer platform, you can basically pick and choose what individual software NeRFs you're using, also known as the methods, to run your models on. Now, when we started off, we were just looking for something very simple. We wanted to see what NeRF Studio was capable of, and so the method we chose was NeRFacto. The baseline, we needed a way to test our models out, and we wanted to see what it would give us. And we noticed, now, these NeRFs, these Neural Radiance Fields, were giving us a lot of weird ghosting and artifacts in negative space, so stuff that wouldn't necessarily exist in real life. So we were looking to try and solve that going forward. And we found one that we thought would potentially solve the problem. NeRF Busters, which in its name was meant to stop any of those artifacts and ghosting from happening when you're creating these fields. Unfortunately, though, NeRF Studio was being developed so quickly and so fast, but by the time we finally got NeRF Busters to really start working, it was already out of date and we had to start updating it again. And we just ended up moving on and switching to another one entirely. See-Through NeRF, which was custom built for underwater objects. Now, it applies an old image filtering algorithm using a depth map to remove some of the tint you're going to see underwater. Now, next slide. What you've seen thus far, this is created using the see-through algorithm. And it's the best result we've had, though there's some minor things I want to point out here. Notice the haze and a little bit of artifacting in places you wouldn't necessarily have seen it on the Silver Comet itself. We realized going forward that our next challenge was to try and see if we could remove that, because this model is wonderful. You've got high detail, you've got a lot of the railings over there, which you wouldn't necessarily get on photogrammetry, but you're going to get some silt in places you wouldn't necessarily have otherwise. Next slide. So now I'm going to show it from a different angle. The more you zoom out from a Neural Radiance field, the more you're going to start getting some things that weren't necessarily there. These heavy clouds were not present underwater. It's not difficult to potentially edit one of these. It's practically, as of right now, with our current status, not something we can currently accomplish to edit these. So what you see right here, when you're putting photos into create a Neural Radiance field, that's what you're going to get. It takes a lot of prep to get these right. Going forward, we're looking at trying to fix that, but this is the current reality of the situation. Next slide. So to solve that problem of getting rid of these weird silty clouds around it, I want to introduce Project GSHARC. We're going to take Gaussian splatting, we're going to apply it to these models, and we're going to get an output that we can hopefully edit. Next slide.
So Gaussian splatting, what is it? Instead of doing the neural component of the neural radiant fields, it takes a sparse point cloud, which doesn't have a lot of points in it, and adds like a little smoothing on top. So each point has more data to it that can make a more complete model. I found this from a 2-minute papers video, very similar to how we found the Neural Radiant Fields videos. I'd highly recommend watching that video if you get a chance. So here's a little bit of a demo of it. You can see the kind of coarseness of the points that we're actually using in this when I drag that slider back and forth. Slide. So how is this different from NeRF? Remember, NeRF is neural, so that's why it's impossible for us to directly edit it, because it's kind of a black box. This being based on a point cloud, it's easy to edit. It can also be viewed on really low-end hardware and can even be rendered live in like kind of interactive environments. And we're actually editing it in this screenshot, and it's being edited in a web browser on a, not too crazy of a computer.
All right, so as a show of hands, who here's used Agisoft Metashape to do photogrammetry process workflows? Okay, awesome, 2, wonderful. So when we made these workflows, we didn't separate it by whether or not you could you wanted to make a neural radiance field or whether or not you wanted to make a Gaussian splat. You can do both with mostly the same workflow. That's how great NeRF Studio is. What we separated it by was whether or not you could align the photos with something called ColMap. Either ColMap will wonderfully align your photos automatically, or you'll have a complete failure and you need to align them elsewhere. So this is the basic overview of what we're doing. But who better to tell you about what's happening here than our good friend Henry, a literal sailor, who's helped us to sailor-proof these workflows as best as possible. Take it away, Henry.
Thank you, Josh. Thank you. So yes, I was a sailor in the Navy. All of our manuals were written at an 8th grade level. All of the fighter jets, all of the complicated equipment. So their task was to write a manual that I could read. Thank you, guys. And they did. They did, and they did very well, because I was able to do it. I felt so proud of myself. So here we have the first step. We get the repos we need from GitHub. We update some things with pip install. Moving on to process 2. There is a cap with the size of the images that we're working with in terms of NeRF Studio. So we have to scale them down, and that's what this process does. We're scaling all of that down, getting it ready for processing. Here we have some ColMap output. So in this instance, ColMap was very successful. 87% of the images were matched. This is very good. Stolt 3D, however, doesn't have that much luck with ColMap, so no problem. We can go into Metashape and manually smooth out those inconsistencies. Having 2 ways of doing it really helps keep it redundant and secure. Redundant in a good way. So we have all of this output now. We have our alignment data. We have transforms.json, which is our positional imaging data. We have sparse point cloud data. And now we have to take all of that and we have to pipe it into the NeRF software. And we do that with the train command. The train command takes all of that and it trains the model. So auto alignment has some inconsistencies with the Stolt and the Silver Comet. They produced wildly different outputs. So again, we can go into Metashape and smooth that out. As you can see, these numbers show the inconsistencies with ColMap. So again, we can use a GUI to do it, but the ColMap process is a lot faster and a lot easier, saving hundreds, on a bigger project, maybe even thousands of man-hours.
To someone who's done, used Agisoft Metashape and you've aligned your photos elsewhere, we have a script that can export those photos straight into this process, do everything we've just told you, maybe skipping a step or 2, training our model, and giving you either a NeRF or a Gaussian splat, depending on what you want. And we successfully did this with the Silver Comet. Now, as any scientists, researchers, or anyone who's dealt with data before, when you start scaling things up from smaller models to larger data sets, you're going to run into some smaller issues. And we're currently working through those right now. So what are we doing next? Well, we're going to work on those bugs, we're going to get a final workflow out, and we're going to be able to apply this to any model in the future going forward. This is how we're going to finish Stolt 3D. We want metrics. When is a photogrammetric model useful? When is a NeRF useful? When is a Gaussian splat useful? I want comparisons. I want to know when something is going to be more efficient. I want to know the trade-offs between each in processing power, speed, quality, etc. I want to take our current workflows. I want to automate them. I want to make them as simple, as easy as possible. I want someone to be able to upload their photos and boom, maybe an hour later, I want you to have your model. I want it to be super easy for anyone to get involved with this. I want to take our input images. I want to filter them. I want to get rid of the tints. I want the post-processing and pre-processing to be simple, easy. Again, so anyone can do this. Again, as far as I'm concerned, this should be as painless as possible for anyone involved, and I want as many people to be involved with this.
Okay, so there's one really big thing I wanted to save to the end, because it sounds like when you're doing this, you have to make some pretty big decisions up front for your projects. But the most important part about this workflow is that you don't have to choose your post method up front. So you can go on your dive, you can enjoy, take those photos, and downstream, you could choose to do traditional mesh photogrammetry, you can choose to do neural radiance, or you could choose to do Gaussian splatting, or if you're wild like us, you can do all three for each project. But I really want to emphasize, you don't have to choose up front because they can all accept a very similar data set. There's ways to optimize for one or the other, but if you're capturing a data set to photogrammetric standards, you're already over the standards needed for the other two. So I want to really emphasize that. It's a very flexible system. Okay, now it's time for 2 and 2. I'm gonna ask for 2 things, and then I'm gonna give you 2 resources. I think I'm supposed to do it the other way around, so I give you a bunch of stuff, then I ask for stuff, and then there's the subtext that, oh, you know, I wanna make it way less awkward. So what I hope to have from some of you is first engagement, and second, funding. I'll start with the funding part, because it's the most awkward. We are not stopping this work, period. We're nonprofit, we're looking for grants and corporate CSR initiatives. That's what I mean. I'm not asking for money in this room. I'm saying if you have an idea of a research grant, an operational grant, some sort of project that's ongoing, or any CSR initiatives that cover teaching middle and high schoolers how to do 3D modeling, please send me a 1-sentence email and we'll set up some time to talk so I know where to direct our grant writers to. I'm not asking for donations from anyone in the room. Thing number 2, engagement. If you would like a full course on this, we're talking 6 hours, a bunch of laptops, some time on Lambda Cloud, which is a supercomputer, and actually doing a start to finish set, send me an email. We'll put you on the pre-release list, so when we do offer a public class, I'll reach out to you first. And then lastly, if you want to have that GitHub repository with a lot of the automation, send me an email. If you're interested in any sort of abstracted service where you have a data set but you need help, send me an email. We're a nonprofit. We're not here to gouge and make a ton of money. We're just here to help the community, and we're here to help kind of teach this methodology. Okay, now for the other 2 where I give you stuff. First of all, this is the time to scan it if you want to see our lab notes. As soon as the phones go down, I'll go to the next slide. Don't worry. But for those who are writing notes, just go to Scuba.Tech. That's the website, Scuba.Tech. You put that in a browser, it's going to take you right to the homepage. On that homepage, all you got to do is click on OSIRIS GSHARC, and you'll have our start to finish lab notes that will walk you through everything we just did, to include what's happening here on the console, to include all those screenshots you saw, and then to include even the live demo portion. It's every command start to finish. If you're in a copy paste kind of mood, you can get away with that and just change the file paths. Okay, last camera went down. Okay, the second thing I'm going to give you is some movies. Right now, Let's Go Explore is our non-monetized YouTube channel. We're mostly focusing on ROV hybrid operations, where we take ROVs and divers, we take middle schoolers and high schoolers with NYSMIA, New York State schools, New York City schools, soon Connecticut schools, and we do all this in a field study environment, and we film it and we make episodes about it. Moving forward, what you just saw, we're going to make something slightly more engaging, and it's going to go up here as well. So if you learn better through video or kinesthetically, consider this. That QR code will simply take you to the channel. It's not monetized. We're not selling anything. We just want to share this. And with that, I want to say thank you. I know we only have about 5 minutes before we really got to be out of here. But if you have questions, or if you think of questions 20 minutes afterward, like I tend to do, you can come find us at booth 240. We're at the end cap on the second row. look for all the robots, all the ROVs, all the robot arms, all the cameras. We're going to have the 3D models out. You'll see this TV again, and you can come and test drive stuff for yourself or just do Q&A. Feel free to stop by. We'll be there until 1600 today. That said, any questions? Yes?
What's the largest data set you've tried running through the NeRF so far?
The largest data set would be the Ford cut on the Stolt 3D, the Stolt de Gali Ford cut. We ran out of video RAM. To expand the I'll just be blunt about it. So to expand the operations, there's two things we need to do. Number one, we need to find a capital grant that'll let us buy a couple A100 or better GPUs. We need a lot more video RAM to crunch this. Number two, we can lease time through Lambda Cloud. They are not a sponsor. If y'all are watching, though, please reach out. You can lease compute on Lambda Cloud, and you can basically have an entire room full of GPUs for $17 an hour. And a render like this might take a few hours, so it's relatively affordable compared to paying a couple $100,000 for GPUs. The largest one that we pulled off successfully on just that discrete one GPU, the RTX 6000, the Quadro series with 24 gigs of VRAM, is the Silver Comet. So a small to mid-size vessel can fit on one very powerful GPU. If you want to do larger than that, you need to be on either GPU cloud systems or you need to have a GPU farm of your own. As of now. That said, that's why I mentioned send me an email if you want some help with a managed service, if you want us to take your photo set and we'll just bill you the cost of the cloud time and like a very small fee for their time off salary. We can help broker that if you just need a cloud to process your photo set and you just want the results, because we understand that building a GPU farm isn't exactly in everyone's interest. Hope I over-answered that one. Next question. Yes, sir.
In the earlier slides, you were talking about LiDAR starting in the edge. Are you looking at integrating LiDAR?
We are. Okay. Yeah, also another, I really don't mean to keep taking this back to funding. If you know of any capital grant initiatives, we are saving up for a LiDAR system as well, and we want to integrate that into the photogrammetric workflow. Although it might be worth experimenting for splatting, because LiDAR, as you know, gives a pretty good point cloud output, and we could take texture data from the photos to color it. So yeah, we are looking to integrate LiDAR. Any other questions? Okay, looks like we covered it pretty thoroughly. Thank you for your time. Thank you for my team. We'll see you outside. Good stuff, man.